Alright, let's go. Number 10. The Lunar Transient Phenomena. For over 4 centuries, humanity has documented something impossible happening on the moon's surface. Flashes of light, glowing regions that shouldn't exist, color changes spreading across crater floors. These aren't ancient myths or blurry photographs from amateur astronomers. They're systematic observations recorded by some of history's most credible witnesses, including William Herschel, the astronomer who discovered Uranus, and Neil Armstrong during the Apollo 11 mission. In 1968, NASA compiled a chronological catalog of reported lunar events. The document, designated Technical Report R277, contained over 1,500 observations spanning from the 1540s to the present day. What makes these reports particularly unsettling is their concentration in specific locations. Aristarchus crater accounts for roughly 30% of all observations. Plato crater and Mare Crisium show similar patterns of recurring phenomena. Whatever causes these events appears to favor certain regions of the lunar surface. The moon should be geologically dead. It has no atmosphere to create weather phenomena, no active volcanism, no tectonic activity. Its surface has remained essentially unchanged for billions of years. Yet observers continue to report temporary flashes, glows lasting minutes to hours, and color changes that defy explanation. Modern automated monitoring systems operated by NASA have confirmed one type of lunar transient: impact flashes from meteorites striking the surface. Since 2005, over 300 such impacts have been documented, each producing a brief flash lasting milliseconds to about 1 second. These impacts occur primarily during meteor shower periods and release energy equivalent to 5 to 500 pounds of TNT. But impact flashes don't explain the historical observations. They don't account for glows lasting 10 minutes. They can't produce the reddish color changes reported across entire crater systems. They don't explain why Apollo astronauts, trained observers with no reason to fabricate reports, described seeing unusual luminescence near specific features. Scientists have proposed outgassing as an explanation. Radioactive decay in the lunar interior produces radon gas that could escape through fissures in the surface, displacing dust and creating visible effects. Apollo instruments did detect trace amounts of radon, but the moon is 4.5 billion years old. Any significant outgassing should have ceased eons ago. The quantities required to explain bright flashes and extended glows seem implausibly large. Some researchers suggest electrostatic levitation of lunar dust. Solar ultraviolet radiation ionizes fine particles, creating electrical charges that could lift dust off the surface. This might explain horizon glows observed by Apollo astronauts. But it doesn't account for the localized intense phenomena reported from Earth-based observations, nor does it explain the historical concentration of events in specific craters. What makes the lunar transient phenomena particularly disturbing is their persistence across centuries of observation, their concentration in repeating locations, and the complete absence of a satisfactory physical mechanism to explain them. Our closest celestial neighbor, the most studied object beyond Earth, continues to display behavior we cannot adequately explain with current physics. Number 9. GCRT J1745-3009. In 2002, astronomer Scott Hyman was analyzing archival data from the Very Large Array Radio Telescope when he discovered something that shouldn't exist. A radio source near the galactic center was emitting bursts of energy with mechanical precision. Every 77 minutes, the source would activate, transmit for exactly 10 minutes, then fall silent for 67 minutes before repeating the cycle. The regularity was absolute, maintained across multiple days of observation. No known astrophysical object behaves this way. Pulsars, the rotating neutron stars that sweep radio beams across space like cosmic lighthouses, spin far too rapidly. Their periods range from milliseconds to about 10 seconds at most. A neutron star rotating with a 77-minute period would be spinning so slowly it defies our understanding of how these objects form and evolve. Binary star systems can produce periodic signals through eclipses or interactions between stellar companions, but their orbital periods typically span hours to days, not 77 minutes. And even those systems show gradual brightness changes as one star passes in front of another, not the abrupt on-off pattern exhibited by GCRT J1745-3009. The source's location adds another layer of mystery. It sits within 10 light-years of Sagittarius A star, the supermassive black hole at the Milky Way's center. This is one of the most extreme environments in our galaxy, a region packed with neutron stars, stellar remnants, and an object subjected to intense gravitational forces. Perhaps the galactic center's unique conditions enable phenomena impossible elsewhere, but that explanation merely relocates the mystery rather than solving it. What makes GCRT J1745-3009 truly unsettling is its transient nature. The source appeared in observations from 2000 and 2001, exhibited its clockwork pattern, then vanished. Follow-up observations with the Very Large Array and other radio telescopes detected nothing. Multiple search campaigns over the years have failed to find it again. Whatever created those impossibly regular bursts either stopped transmitting or moved beyond detection capability. The discovery prompted searches for similar objects. Astronomers found 4 more sources with comparable characteristics, all designated GCRT J1746, with different coordinate suffixes, all near the galactic center, all exhibiting periodic bursts with durations of minutes to tens of minutes, all transient. These additional detections suggest GCRT J1745-3009 isn't unique, but rather represents a new class of galactic center phenomena we don't understand. Theoretical models have struggled to explain the observations. An exotic binary system containing a white dwarf or neutron star could potentially produce 77-minute periodicity if the orbit is extraordinarily tight, but the emission mechanism remains unclear. Magnetic field interactions between binary companions might generate radio waves, but the 10-minute duration and sharp on-off transitions don't match predictions. Some astronomers have proposed unusual magnetar activity, perhaps involving a neutron star with an anomalous magnetic field geometry that creates narrow beams of radio emission. But magnetars typically show irregular flares, not metronomic regularity. The most honest assessment is that we don't know. The 77-minute period combined with 10-minute burst duration and transient behavior creates a pattern that fits no existing astrophysical model. Somewhere near the center of our galaxy, at least 5 objects have exhibited clockwork timing that suggests a physical mechanism we haven't discovered, operating in an environment we don't fully understand, producing radio signals that appear and vanish on timescales we cannot predict. Number 8, the cold spot. In 2004, astronomer Lawrence Rudnick and his team were analyzing data from NASA's Wilkinson Microwave Anisotropy probe when they noticed something impossible. A region of space in the constellation Eridanus, spanning roughly 1 billion light-years across, appeared significantly colder than its surroundings. This wasn't a subtle variation. The cold spot registers approximately 70 microkelvins below the expected temperature of the cosmic microwave background, the afterglow of the Big Bang that fills all of space. The statistical improbability is staggering. Computer simulations of the early universe rarely produce such features, and when they do, the anomalies are typically smaller and less pronounced. Depending on the analysis method, the probability of the cold spot appearing by random chance ranges from roughly 1 in 370 to 1 in 50,000. These are the kinds of odds that make scientists question whether they're looking at a genuine cosmological anomaly or a flaw in their understanding. In 2013, the European Space Agency's Planck satellite, equipped with more sensitive instruments and higher resolution capabilities, confirmed the cold spot's existence. This was no measurement error, no artifact of aging equipment or flawed data processing. Independent observations with entirely different technology detected the same massive cold region in the same location. The discovery prompted astronomers to search for an explanation. In 2015, researchers mapping the distribution of galaxies in the cold spot's direction found a possible supervoid, a region of space with approximately 20% fewer galaxies than average, stretching nearly 1 billion light-years across and located roughly 3 billion light-years away. As light from the cosmic microwave background passes through this underdense region, it loses energy climbing out of the void's gravitational potential. Well, a phenomenon known as the integrated Sachs-Wolf effect. This would make the CMB appear colder in that direction. The problem is that the supervoid, even if real and properly characterized, can only account for about 30% of the observed temperature deficit. The remaining 70% has no explanation. Either there's additional structure we haven't detected, our measurements of the void's properties are significantly wrong, or something about this region of space fundamentally contradicts our models of cosmic structure. What makes the cold spot particularly unsettling is its challenge to the cosmological principle, the foundational assumption that the universe should look statistically the same in all directions when viewed on the largest scales. The existence of such a massive, improbable anomaly suggests either the universe has structure and variation we don't understand, or we're witnessing something from the universe's earliest moments that inflation theory cannot adequately explain. Some theorists have even proposed the cold spot could be evidence of a collision with another universe during the first fraction of a second after the Big Bang, though most cosmologists consider this speculation too far removed from testable science. What remains is a billion light-year wide region of space that shouldn't exist, according to our best cosmological models, confirmed by multiple independent observations, with no satisfactory explanation despite 2 decades of research. Number 7. The WOW signal. On August 15, 1977, at 11:16 p.m. Eastern Time, the Big Ear radio telescope in Ohio detected something extraordinary. Astronomer Jerry Amon was reviewing computer printouts of the previous night's observations when he saw a sequence of values so unusual he grabbed a red pen and circled them, writing a single word in the margin: wow. The signal that produced his reaction lasted exactly 72 seconds. The maximum duration Big Ear could observe any point in the sky as Earth's rotation carried the telescope's field of view across space. What made the WOW signal remarkable wasn't just its intensity. Though at 30 times stronger than the background noise, it was impossible to miss. It was the signal's characteristics. The emission occurred at 1420 megahertz, the frequency associated with neutral hydrogen, the most abundant element in the universe. This is precisely the frequency scientists have long predicted would be ideal for interstellar communication. It's protected by international agreement from terrestrial use, making interference unlikely. Any technological civilization attempting to broadcast across space would logically choose this universal frequency. The signal was narrowband, concentrated in a frequency range far tighter than natural cosmic sources produce. Pulsars, quasars, and other known radio emitters create broadband emissions spread across wide frequency ranges. Natural masers can produce narrower signals, but not with the characteristics exhibited by the WOW signal. The emission appeared to originate from the direction of Sagittarius, specifically near the star group Chi Sagittarii, though the telescope's resolution couldn't pinpoint an exact source. For over 45 years, astronomers have attempted to detect the signal again. The Big Ear telescope continued operating until 1997, repeatedly targeting the same region of sky. Other observatories have conducted follow-up searches using more sensitive equipment. In 2012 and 2020, deliberate transmission campaigns beamed messages toward the signal's apparent origin. Nothing has ever been detected again. The WOW signal remains a singular event, unrepeated and unexplained. Scientists have systematically ruled out terrestrial sources. The signal's frequency, duration, and intensity profile don't match satellite transmissions, aircraft, or ground-based interference. The way the signal strength rose and fell over 72 seconds precisely matched the telescope's antenna pattern as it swept across a fixed celestial point, confirming the source was astronomical, not local. In 2017, researcher Antonio Paris proposed the signal might have been caused by a passing comet releasing hydrogen gas. But this theory was widely criticized and largely dismissed because comets don't produce the required radio signal strength at that frequency. What remains is a signal that perfectly matched predictions for extraterrestrial communication, detected once in over 4 decades of searching, never repeated, never explained. The WOW signal stands as the most compelling candidate for contact ever received. A 72-second glimpse of something that might have been first contact, or might have been a natural phenomenon we still don't understand, leaving us suspended between wonder and uncertainty. Number 6. The Kuiper Belt Cliff. Beyond Neptune's orbit, approximately 2.8 billion miles from the Sun, lies the Kuiper Belt, a vast region of icy bodies left over from the solar system's formation. For decades, astronomers assumed this population of frozen worlds would gradually thin out as distance increased, a smooth decline reflecting the density of the primordial disk from which planets formed. Instead, between 2019 and 2020, analysis of multiple survey programs revealed something profoundly wrong. At approximately 48 to 50 astronomical units from the Sun, roughly 4.6 billion miles out, the population doesn't gradually decline. It drops off a cliff. Within just a few astronomical units, the density of Kuiper Belt objects plummets by 90%. This isn't a gradual thinning that might result from normal planetary formation processes. It's a sharp boundary, an edge where objects simply stop existing in the numbers they should. Standard models of how solar systems form predict nothing like this. The protoplanetary disk that birthed our planets should have created a smooth distribution of material extending far beyond this arbitrary line. Yet something either swept this region clean after the planets formed, or prevented objects from accumulating there in the first place. The most popular explanation involves an undiscovered planet. In 2016, Caltech astronomers Konstantin Bettigin and Mike Brown proposed the existence of Planet 9, a world perhaps 5 to 10 times Earth's mass, orbiting at extreme distance. Their hypothesis emerged emerged from observing the strange clustering of orbital parameters among extreme trans-Neptunian objects, bodies with orbits extending far beyond Neptune. These distant worlds show a suspicious alignment in their orbital orientations, as if something massive is shepherding them into similar paths. Computer simulations suggest a large planet in a highly elliptical orbit could create both this clustering and the Kuiper Belt's sharp edge through gravitational perturbations over millions of years. But searches for Planet 9 have found nothing. If it exists, it's either extremely far away, making it incredibly faint, or orbiting in a region of sky that's difficult to survey. The planet remains hypothetical, inferred only from its gravitational effects, rather than direct observation. An alternative explanation suggests a passing star during the solar system's infancy gravitationally truncated the primordial disk. Our sun likely formed in a stellar nursery, a cluster of young stars where close encounters were possible. A star passing within a few hundred astronomical units could have stripped away material from the outer disk, creating the sharp edge we observe today. Each explanation requires specific, improbable conditions. Either an undetected planet lurks in our solar system's outer darkness, massive enough to reshape the architecture of distant orbits, or a stellar encounter during the first 100 million years happened to occur at precisely the right distance and angle to sculpt the Kuiper Belt's boundary. Both scenarios are possible, neither is confirmed. What remains is a massive structural feature in our own cosmic backyard, a boundary that shouldn't exist according to standard formation theory, raising the disturbing question of what other fundamental aspects of our solar system we might be misunderstanding. Number 5. Fast radio, burst FRB 2002000120E. On January 20th, 2020, the Chime Radio Telescope in British Columbia detected a millisecond duration burst of radio energy from the nearby galaxy M81, located approximately 12 million light-years from Earth. This proximity made it the closest fast radio burst ever detected with a confirmed host galaxy, close enough to pinpoint its exact location with unprecedented precision using radio interferometry techniques. What astronomers found shattered every existing theory about what creates these mysterious cosmic phenomena. The source wasn't located in a region of active star formation, the violent stellar nurseries where massive young stars explode as supernovae. It wasn't associated with a young energetic galaxy undergoing rapid evolution. The burst originated from a globular cluster, an ancient collection of stars orbiting M81's outer regions. Globular clusters are cosmic retirement homes. They contain stars over 10 billion years old, formed when the universe was young and galaxies were first assembling. Star formation in these clusters ceased billions of years ago. They should be magnetically dead, populated by stars in their final evolutionary stages, with no capacity for the extreme energetic events required to produce fast radio bursts. Every proposed mechanism for generating FRBs requires young stellar remnants or catastrophic events. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, were the leading candidate. But magnetars form from massive stars that exploded relatively recently, typically within the last few thousand years. Globular clusters haven't produced such stars for eons. Colliding neutron stars might create FRBs, but such mergers should be extraordinarily rare in globular clusters, and the repeating nature of this source rules out one-time collision events. Supergiant pulsars, young stellar cores spinning hundreds of times per second, don't exist in ancient stellar populations. The discovery forced a fundamental reconsideration of FRB origins. If globular clusters can host repeating FRB sources, then the formation mechanism must be far more diverse than scientists believe. Perhaps unusual binary evolution in dense stellar environments can create magnetar-like objects through exotic pathways. Maybe a white dwarf accreted enough material from a companion star to collapse into a neutron star, forming a magnetar billions of years after the cluster's birth. Or possibly FRBs represent multiple distinct phenomena that happen to produce similar observational signatures, convergent events arising from completely different physical processes. What makes FRB 2002000120E particularly unsettling is its challenge to the assumption that we understand stellar evolution and the environments capable of producing extreme magnetic phenomena. The burst itself is unremarkable compared to other FRBs, repeating irregularly with variable energy, the kind of behavior seen in other repeating sources. But its location in an ancient globular cluster reveals our theories about what conditions can generate these cosmic shrieks of radio energy are fundamentally incomplete, demonstrating that even environments we consider well understood and magnetically dormant can harbor phenomena that defy our models of how stars live, die, and leave behind compact remnants capable of violence. Number 4. The axis of evil. In 2005, astronomers Kate Land and João Magejo were analyzing temperature fluctuations in the cosmic microwave background when they discovered something so disturbing they gave it an ominous name, the axis of evil. The largest structures visible in the CMB, temperature variations representing the seeds of galaxy formation imprinted when the universe was only 380,000 years old, are mysteriously aligned with each other. Even more unsettling, they're aligned with the plane of Earth's solar system and the equinoxes, geometric features that didn't exist until 13 billion years after the CMB was created. This shouldn't be possible. The cosmological principle, one of the foundational assumptions of modern cosmology, states that on large scales the universe should look the same in all directions. There should be no preferred orientation, no cosmic compass pointing toward Earth. The CMB represents a snapshot of the universe's structure from an epic billions of years before our solar system formed. The idea that primordial temperature fluctuations spanning billions of light years could somehow correlate with the orientation of our planetary system violates everything we understand about cosmic structure and causality. The discovery was initially met with skepticism. Perhaps it was a measurement error, an artifact of data processing, or contamination from foreground sources like the Milky Way's own emission. But in 2013, the European Space Agency's Planck satellite, using entirely different instruments and more sophisticated analysis techniques, confirmed the alignment. Independent observations with better technology detected the same impossible correlation. The axis of evil is real. The alignment specifically affects the quadrupole and octupole moments of the CMB, technical terms describing the largest scale temperature variations across the sky. These aren't subtle effects requiring statistical mining to detect. They're among the most prominent features in the temperature map, and their axes of symmetry point in directions that correlate with local solar system geometry. The statistical probability of this occurring by chance varies depending on calculation methods, but most estimates place it somewhere between 1 in 370 and 1 in 50,000. Proposed explanations struggle to account for the observations. Some scientists argue it must be foreground contamination, emission from dust, or other sources in our galaxy that hasn't been properly removed from the data. Despite extensive efforts to clean the signal, the alignment persists. Others suggest it's simply an unlucky statistical fluctuation, a case of observing patterns in random data. With millions of resolution elements in the CMB map, some will appear anomalous, but the specific alignment with solar system geometry seems too precise to dismiss as coincidence. More exotic explanations invoke non-standard cosmology. Perhaps the universe has a preferred direction, violating the cosmological principle. Maybe the topology of space is more complex than we assume, with the universe wrapping back on itself in ways that create correlations between distant regions. Some theorists have even suggested the axis of evil could be evidence of a collision with another universe during the inflationary epoch, a bruise on the fabric of space-time from contact with a neighboring bubble universe in a cosmic multiverse. What makes this mystery particularly profound is that it strikes at the heart of our understanding of the universe's structure and our place within it. If the alignment is real and not an artifact, it suggests either our most fundamental cosmological assumptions are wrong, or our location in the universe is somehow special, in ways that contradict the Copernican principle that has guided astronomy for centuries. How can structures formed 13 billion years before Earth existed show geometric alignment with our solar system's orientation? Number 3. The eROSITA bubbles. In December 2020, the eROSITA X-ray telescope aboard the Russian-German Spectre RG spacecraft released images that revealed something shocking about our home galaxy. Extending approximately 50,000 light-years above and below the Milky Way's center were two enormous structures, symmetric bubbles of million-degree plasma emitting X-rays across a significant fraction of the sky. Each bubble stretches roughly 3 times farther than the previously discovered Fermi bubbles. Gamma-ray structures found in 2010 that astronomers thought represented the largest features associated with our galaxy's core. The bubbles' sharp, well-defined edges suggest they weren't formed through gradual processes, but rather created by a single catastrophic event, an explosion at the galactic center that occurred approximately 15 to 20 million years ago. The energy required to inflate structures this massive is staggering, equivalent to roughly 100,000 supernovae detonating in a concentrated region over a relatively short cosmic timescale. That's between 10 to the 56th and 10 to the 57th ergs of total energy, more than our sun will produce over its entire 10 billion year lifetime. Yet we have no adequate explanation for what caused such a massive energy release. Sagittarius A star, the supermassive black hole at the Milky Way's center, is currently in a relatively quiet state. It's not actively consuming large amounts of material, not producing the violent outflows typical of active galactic nuclei in other galaxies. The black hole's mass is approximately 4 million times that of our sun, large enough to produce dramatic effects if it were actively feeding. But all observations indicate it's been dormant for millions of years. Perhaps 15 to 20 million years years ago, something changed. A massive gas cloud might have fallen into the black hole, or an entire star cluster could have been consumed, triggering a brief period of intense accretion. As matter spiraled inward, friction and magnetic fields would have heated it to millions of degrees, producing jets of material and radiation that punched through the galaxy's disk and inflated the bubbles we observe today. This scenario is plausible, but requires a very specific sequence of events and an amount of material consumption that seems difficult to achieve, given current models of galactic center dynamics. An alternative explanation involves an unprecedented burst of star formation at the galactic center. If conditions somehow triggered the rapid formation of thousands of massive stars in close proximity, their subsequent explosions as supernovae over a few million years could have injected enough energy to create the observed structures. But the Milky Way isn't currently undergoing a starburst phase, the kind of intense star formation seen in galaxies like M82, where similar bubble structures have been observed. What could have triggered such a dramatic episode of star formation, and why did it end? The most likely scenario combines both mechanisms. Perhaps a massive inflow of gas both triggered star formation and fed the supermassive black hole, creating a hybrid event where stellar explosions and black hole accretion work together to inject energy into the galactic halo. But this explanation remains speculative, constrained by the limited evidence available from structures that formed millions of years ago and located 26,000 light-years away at our galaxy's center, a region obscured by dust and difficult to observe across most of the electromagnetic spectrum. What remains certain is that something happened at the heart of our galaxy, an event powerful enough to reshape the structure of hot gas throughout the Milky Way's halo, and we can only observe its aftermath without fully understanding its cause. Number 2. Tabby's star. In 2015, astronomer Tabitha Boyajian was analyzing data from NASA's Kepler Space Telescope when she noticed something unprecedented. A star designated KIC 846-2852, located approximately 1,470 light-years away in the constellation Cygnus, was displaying bizarre fluctuations in brightness, unlike anything observed in the hundreds of thousands of other stars Kepler had monitored. The star would randomly dim by up to 22%, a massive loss of light that defied every conventional explanation. When planets pass in front of their host stars, they cause predictable dips in brightness. Jupiter, the largest planet in our solar system, blocks only about 1% of the sun's light during a transit. Even the most favorable planetary configurations produce dimmings of 2% at most. Tabby's star was losing more than a fifth of its light in irregular patterns, with dimming events lasting anywhere from days to weeks, with no discernible periodicity. These weren't the regular clock-like transits of orbiting planets. They were chaotic, unpredictable, and far too deep. Further investigation revealed an even more disturbing pattern. Analysis of archival photographic plates spanning over a century showed that Tabby's star has been gradually dimming by approximately 14% since the late 1800s. This long-term fading is impossible to explain through normal stellar evolution. Stars don't naturally lose 14% of their brightness over a century unless something catastrophic is happening, and nothing about Tabby's star suggests it's in a state of rapid change or instability. The dimming shows a peculiar wavelength dependence. Blue light is affected more than red light, indicating that whatever is blocking the star's light consists of particles larger than interstellar dust, but smaller than typical cosmic dust grains. This rules out many potential explanations while pointing toward extremely fine material, perhaps micron-sized particles, distributed in unusually large and irregular structures. Proposed natural explanations have included swarms of comets, though the sheer quantity required seems implausible. Dense clouds of dust might explain some observations, but where such dust originates and why it's arranged in such massive irregular clumps remains unexplained. Some scientists have suggested the star recently consumed a planet, with the debris creating the observed dimming, but this scenario struggles to account for the century-long brightness decline recorded in historical data. The hypothesis that captured public imagination involved Dyson spheres, or megastructures, hypothetical constructions built by advanced civilizations to capture a star's energy output. If an alien civilization were in the process of constructing such a structure, we might observe exactly what Kepler detected: irregular dimming events as massive objects move around the star in complex non-planetary orbits, combined with long-term dimming as an increasing fraction of the star's light is captured or blocked. Most astronomers favor natural explanations, and several research teams continue monitoring Tabby's star with ground-based telescopes. Additional observations have provided more data on the dimming event's characteristics, but they haven't resolved the fundamental mystery. Multiple subsequent analyses have proposed variations on dust-based explanations, each attempting to account for the specific wavelength, dependence, and irregular timing of the dimming events, yet none has achieved consistent consensus acceptance in the scientific community. What makes Tabby's star genuinely unsettling is that it remains the only star among the hundreds of thousands observed by Kepler that exhibits this specific behavior. If the explanation is natural, why haven't we found other examples? If it's a rare but natural phenomenon, we should eventually detect similar stars. If it's an artifact of measurement or data processing, why does it persist across multiple independent observation methods? The star continues to be monitored, its irregular flickering challenging our understanding of what constitutes normal stellar behavior, and remaining a cosmic enigma that forces us to confront how little we truly know about the diversity of phenomena that exist in our galaxy. Number 1. The Oumuamua acceleration anomaly. On October 19, 2017, astronomer Robert Warwick was reviewing images from the Pan-STARRS 1 telescope in Hawaii when he spotted something moving against the background of distant stars. Within hours, astronomers realized this wasn't an asteroid or comet from our solar system. Its trajectory was hyperbolic, entering from interstellar space at 26 kilometers per second, too fast to be gravitationally bound to the sun. Humanity had detected its first confirmed visitor from another star system, an object that would be named Oumuamua, Hawaiian for scout, or messenger from afar arriving first. The object was strange from the start. Its brightness varied by a factor of 10 as it tumbled through space, suggesting an extremely elongated shape, perhaps 10 times longer than it was wide. Nothing in our solar system has such an extreme aspect ratio. Observations revealed a reddish surface consistent with organic compounds baked by cosmic radiation during millions of years traveling through interstellar space. Oumuamua was tumbling chaotically, rather than rotating smoothly, indicating it had been ejected violently from its home system. But the real mystery emerged months after the object had already passed closest to the sun and was speeding away into the outer solar system. Detailed analysis of its trajectory revealed something impossible. Oumuamua was accelerating, moving faster than gravity alone could account for. The acceleration was small but measurable, approximately 5 times 10 to the negative 6 meters per second squared, and it pointed directly away from the sun. When comets approach the sun, they accelerate due to outgassing. Solar heat vaporizes ice beneath the surface, creating jets of gas and dust that act like tiny rocket engines, pushing the comet in specific directions. Astronomers have observed this behavior in thousands of comets. It's predictable, well understood, and always accompanied by a visible coma and tail as the outgassing material reflects sunlight. Oumuamua showed no such activity. Despite passing within 0.25 astronomical units of the sun, closer than Mercury's orbit, and experiencing intense solar heating, the object exhibited no detectable outgassing, no dust tail, no gas emissions of any kind. Yet it accelerated anyway. Every proposed natural explanation struggles with the observations. Harvard astronomer Darrell Seligman suggested Oumuamua might be composed of hydrogen ice, which would sublimate invisibly without creating a visible tail. But hydrogen ice is extraordinarily fragile, sublimating at temperatures far below what Oumuamua would have experienced during millions of years, traveling through interstellar space, exposed to starlight and cosmic rays. How such an object could survive the journey to our solar system remains unclear, and no formation mechanism has been identified that could create hydrogen icebergs in planetary systems. Another hypothesis proposed that Oumuamua was a fragment of nitrogen ice similar to the material covering Pluto's surface, broken off from an exoplanet and ejected into interstellar space. Nitrogen ice could potentially sublimate with low visibility while still producing enough thrust to explain the acceleration. But this scenario requires very specific conditions. The fragment would need to originate from a Pluto-like world, be ejected with precisely the right velocity, and retain enough nitrogen ice over millions of years to produce observable acceleration when entering our solar system. The hypothesis is plausible but requires an unlikely chain of circumstances. Some researchers have suggested Oumuamua might be an extremely low-density aggregate of dust, a cosmic dust bunny held together by weak forces. Such an object could have a large surface area relative to its mass, making it susceptible to radiation pressure from sunlight, which might explain the acceleration without requiring outgassing. But whether such fragile structures could survive the journey through interstellar space and the stresses of tumbling rotation remains questionable. Harvard astronomer Avi Loeb has maintained a controversial position since the acceleration was discovered. He argues that based purely on the observational data, artificial origin cannot be definitively ruled out. A thin light sail, perhaps just fractions of a millimeter thick, but hundreds of meters across, pushed by radiation pressure from sunlight, would exhibit exactly the acceleration profile observed, smooth, consistent, pointing away from the sun, with no visible emissions. Loeb emphasizes he's not claiming Oumuamua is alien technology, merely that the hypothesis fits the data and deserves consideration alongside natural explanations that also have significant problems. Most astronomers reject the artificial hypothesis, considering it an unnecessary invocation of extraordinary explanations when more mundane answers like likely exist. The scientific community generally favors some combination of exotic ice composition or unusual material properties that haven't been fully characterized. But the debate continues because none of the proposed natural mechanisms fully satisfy all the observations without requiring special pleading or unlikely conditions. Oumuamua is now beyond the orbit of Saturn, traveling at over 26 kilometers per second relative to the Sun, never to return to the inner solar system. It's too faint to observe even with the most powerful telescopes. We had only a few weeks to study it before it vanished into the cosmic dark, and we weren't prepared. No spacecraft could be launched quickly enough to intercept it. We could only watch it leave, carrying its secrets with it. The first confirmed interstellar object to visit our solar system arrived, exhibited behavior that contradicts our understanding of natural objects, and departed before we could adequately study it. We're left with fragmentary data, competing theories, and the unsettling knowledge that we fundamentally don't understand what kinds of objects drift through the space between stars. Oumuamua's 11-day observation window provided a glimpse into interstellar populations we've only theorized about, revealing that the first example we detected was so unusual that years later, scientists still cannot agree on what it was, how it formed, or why it accelerated without visible means of propulsion. The universe sent us a messenger, and we couldn't decipher its message before it disappeared back into the void.